Hello, we are MSD Team 22652, and our project is ConcRIT 3.0, a small-scale concrete 3D printer. Many senior design projects have the desire to make prototypes out of concrete. However, traditional methods of using wooden molds are extremely expensive and time-consuming, as the mold is often destroyed in the creation of a single prototype. Having the ability to rapid prototype can lead to more repeatable prototypes that take less time and are less expensive.
This is the third iteration of the printer's design. The printer had two main issues our team was set to address. The first issue was XYZ movement for the printer. Motors in the Z direction were binding and the movement was unreliable. The other issue was the failure to reliably deliver concrete to the print head. There was no system in place to pour concrete and have it print out the nozzle. The previous solution was to directly feed concrete in the nozzle by hand, which is not sustainable. In addition, we were tasked to integrate a slicer to 3D print custom parts.
For the motion system, our Cartesian coordinate system is used. Remove the y-axis degree of freedom from the print head and add it to the print bed. This was done to reduce the range that the concrete delivery tube needs to reach, and also increase the stability of the print head gantry. When moving the y-axis to the print bed, we had to replace the stepper motors with geared versions so that they could move the extra weight of the print bed and the concrete. The stepper motors that drive the movement system are connected to the Duet 3D controller board.
For the concrete delivery system, we expanded upon the direct extruder system from the previous team by adding a Bowden extruder at the topper. This extra extruder is there to keep the concrete mixed and to help push the concrete down a tube and deliver it to the print head's original extruder. Both of these consist of DC motors connected to 3D printed augers, which push the concrete down. The hopper was designed so that the Bowden extruder can be easily removed for cleaning. The motors are controlled by dedicated motor controllers, which take in input PWM signals from the Duet board.
For the slicing solution, we use the Kira slicer. The slicer produces G-code that can be uploaded to the Duet web interface, which is how users interact with the printer. We created a custom profile for our printer. We also made a custom profile for our concrete mixture, specifying its flow rate and density, and a third custom profile for the printing information, calibrating settings like layer height and printer speeds. The Duet web interface allows the user to manually control the printer, as well as start and stop prints.
We would like to give a special thanks to our customer, Sarah Brunell, and our guides, Oliver Miller and John Wellen. Jan Manetti, the machine shop supervisor, gave us access to work in the soils and materials lab. Gary Houdenis helped us with welding the hopper and hopper frame. The Fab Lab helped with 3D printing plastic parts used in our project. Finally, we want to thank our sponsor, Klein Steel, who generously donated the sheet metal used for fabricating the hopper.